Okay, Algebra 2, this is our review 2.4 for the assessment that comes up on linear programming. So remember, we had 3 lessons in this unit, okay? So the first day, we did things related to linear programming that did not involve word problems. How to graph a system of linear equalities, how to create the feasible region, finding the vertices, and one of the skills you need is when 2 lines intersect, how do you find that intersection, either graphically or algebraically or using your TI Inspire, which you'll have for this entire test, and then evaluating an objective function to minimize or maximize it. Those skills then just moved forward into word problems. And then everything we did in word problem was, like every problem we did, define your variables. Once you get that, create your objective function you're trying to maximize or minimize. Then list all of your constraints. Graph the feasible region, which includes, lines that are intersecting, finding the region. Once you get that, finding your vertices, and then testing the objective function and answering the question. Words and numbers go into the answer of each of these questions. So let's take a look and see what we have here. This test will be sort of like this review. You'll have a couple of word problems. I look at this, the problem has a lot of words, it's really long. I can just go straight to the question. How many hours should each machine be operated? Okay, then I look and say, well, each machine, how many machines are there? There's machine A and machine B. So I'm going to let A equal the hours of machine A, and I'm going to let B equal the hours of machine B. Once I do that, I know that this is A, this is B. I'm always consistent. This is the A axis, and this is the B axis. Also, once I do that, I know my objective function is going to have an A and a B in it. Okay. What is my objective function? What am I trying to do here? I'm trying to minimize the expense. So I want to minimize my expense. So my expense is going to be a function that equals. Now, somewhere in that problem, it tells you the expenses of machine A and B. I see that it takes $28 to run machine A, and it takes $25 to run machine B. Now, what are my constraints? It looks like I have constraints that are around vanilla and chocolate. So, what is my limit around vanilla? So it says I must produce at least 60 gallons of vanilla. So that means the smallest number of vanilla gallons is 60, and at least 100 gallons of chocolate. So I have to produce at least this amount, okay? Then I just go look and see, what does it tell me about machine A? Machine A can produce 4 ounces of vanilla, and it can produce 5 gallons of chocolate. And then, sorry, let me write that. Machine A can do 4 gallons of vanilla and 5 gallons of chocolate, so it's this. Machine B can produce 3 gallons of vanilla and 10 gallons of chocolate. And that gives me all of my constraints, and I'm ready to move to graphing. So, my constraints: A, greater than or equal to 0, B, greater than or equal to 0, and then I've got these 2 other constraints: 4A plus 3B greater than or equal to 60, and 5A plus 10B greater than or equal to 100. If A is equal to 0, then B is equal to 20. If B is equal to 0, then A is equal to 15. And in the next one, A and B, if A is equal to 0, B is equal to 10. If B is equal to 0, A is equal to 20. Okay, so I need to be able to scale to 20 in both cases. So so if this is 0, I could have 5, 10, 15, and 20, and the same thing here. 5, 10, 15, and 20. So I need to find out what 0, 20 is right here, and 15, 0 is right here. Draw a line that connects those two. Okay, and now for the green line is 0, 10, and 20, 0. And if I connect those two, okay, and now it looks like according to these inequalities right here, I'm shading above both of those lines. So if I shade above both of those lines, I get this kind of feasible region. Those are the only points that are above both the green and the blue lines. So my vertices, I'm going to have 1, 2, 3 different vertices, okay? So my vertices are going to be at 0, 20, at 20, 0, and then where do these two lines intersect? So then I just need to put in my calculator where those two lines intersect. So if I go to my calculator, menu, algebra, solve system, 2 variables, 2 equations. My variables are what? A, comma, B, okay. And so I've got 4A plus 3B equals 60, and 5A plus 10B equal 100, and hit enter, and I get 12.4 coming back as the answer. So my graph was almost close enough, but not quite. So this is 12.4, and that's what, 20, 0. And then up here was 0, 20. So let's go here. 12.4 is my other vertex. So remember, I wanted to minimize the cost. The cost was what? Our expense, 28A plus 25B. So E, my expense, was 28A plus 25B. Let me double check that, 28, 25. So I just need to figure out what is my expense at 0, 20. What is my expense at 20, 0? And what is my expense at 12, 4? So this is going to be 25 times 20, which is 500. And this one is going to be 28 times 20, which is 560. And the next one is going to be 28 times 12 plus 4 times 25. So 28 times 12 plus 4 times 25 is 100. Is 436. So which of these is the minimum expense? So go back to your question before you're done. The question was, how many hours should each machine be operated to fulfill the contract at minimal expense? So they did not ask me the minimum expense, but I know that I need to operate, so 12 hours for machine A and 4 hours for machine B to minimize the expense. And if the question were to ask you the minimum expense, since you've already found it, is $436. Okay? Gauss has started a lawn service. He has 2 different lawnmowers. The regular lawnmower can mow 4 acres an hour at an hourly cost of $4. The super lawnmower can mow 6 acres per hour at a cost of $3. You've accepted a job that requires you to mow at least 12 acres of pasture and provide the clippings for livestock. The regular mower can generate 4 bags of clippings per hour. The super mower can only generate 2 bags of clippings per hour. You've guaranteed you will produce at least 8 bags of clippings per hour. How many hours should you run each mower to minimize hourly cost? Now this one I gave you a little bit of a head start. How many hours should you run each mower? I've already defined the variables, R and S, okay? So regular mower and super mower. Now, the objective function, I'm trying to minimize the cost. So the cost is going to be something R plus something S, okay? So how much does it cost to run the regular mower? So the regular mower runs at an hourly cost of $4, and the super mower runs at a cost of $3, okay? So that's my cost function that I'm trying to minimize. Now, what are our constraints? Okay, so if I look at this, I've got my regular mower, and I have my super mower, okay? And then I've got some kind of limit that I have to tend to. What are the constraints that I have? Well, it looks like how much it can mow, acres per hour, and because I've told that I have to mow at least 12 acres, at least 12. So at least 12 means that that's the smallest that it can be, and I have to generate at least 8 bags of clippings. So at least 8 bags of clippings. So this is the acres, and these are the clippings. So what is the rate of acres for the regular mower? The regular mower can do 4 acres, okay? And then the super mower can do, what, 6 acres? And then if I look at clippings, the regular can generate 4 bags of clippings, and the super can generate 2 bags of clippings. And now I'm good to go with this problem. So let's take a look. My constraints are greater than equal to 0. S greater than equal to 0. Okay, I've got the R and the S axis there. My 2 lines will be 4R plus 6S greater than equal to 12, and 4R plus 2S greater than equal to 8. Find my intercepts. So R and S. If R is 0, S is 2. If S is 0, R is 3. And down here, if R is 0, S is 4. If S is 0, R is 2. So it looks like I need to scale up to 4. So I'm going to spread this one out. So I'm going to say 1, 2, 3, 4. 1, 2, 3, 4. You want to scale and use as much of this grid as you can. So 0, 2 is right here. 3, 0 is right here. A line will connect both of these points. and the green line, 0, 4, and 2, 0 is right here. Line will connect both of these points. Okay, and I'm shading above both of these lines, so my feasible region looks like this. So vertices right there, intersection of these two lines, and right here. So the first one is 0, 4. The next one is 3, 0. And then I got to figure out where these two lines meet. Okay, so I'll go to my calculator just to be sure. And we will do that. So let's go to our calculator. Menu, algebra, solve system, two equations, two variables. My variables happen to be what? R and S. So R, comma, S, and OK. So it's 4R plus 6S equal 12, and 4R plus 2S, 4R plus 2S equal 8. And if I solve that, I get 3 halves 1. So this is the point 3 halves 1, or 1.5, 1. Those are my vertices. So my vertices are 0, 4, 3, 0, and 1.5, what did I say it was? 1.51. Okay. And I'm trying to minimize my cost. And what is it? 4 and 3. So my cost function so the cost at 0, 4, the cost at 3, 0, and the cost at 1.5, 1. So this is going to be 3 times 4, which is 12. This next one is going to be 4 times 3, which is 12. And the last one is going to be 4 times 1.5 plus 3 times 1. This is 6 plus 3, which is 9. So that's my minimum. And so what do they ask for? How many hours should you run each mower to minimize the hourly cost? So I need to run the regular for 1.5 hours and the super for 1 hour to minimize my cost. And if they ask you for the minimum cost per hour is $9 in that scenario. Okay. You might have something that comes up with a matrix. Solve this equation for x, y, and z. So here's my x. So I've got this equation. Okay, so this is a 2 by 2, 2 by 2, 2 by 2. I know that 2x plus 7 has to equal 15. Okay, by looking at this matrix. So I get 2x plus 7 equal 15. If I look at the y, 2 times 2 times 2 plus y plus 5 has to equal 7. So 2 times 2 plus y plus 5 equals 7. If I look at my equation for z, z is this last element right over here. So I see that 2 times 9 plus negative 9 equals z. I just solved these equations. This tells me that 2x equals 8 x equal 4. This one tells me that y plus 9 equals 7, or y equals -2. And the next one is what? This is 18 minus 9. This just gives me z equals 9. Okay? So just basic property of equations, equality and adding matrices. The next one, I give you a feasible region but no word problem. So I say, here's my objective function. Where is the function maximized and what is the maximum value? So I've got 1, 2, 3, 4 vertices. So I just need to evaluate this function at all 4 vertices. So I need to find P at what, 0, 120, P at 80, 120, and then P of 150, 50, and P of 150, 0. Okay, so this is going to be 3 times 0 plus 4 times 120, which is 480. The next one is going to be 3 times 80 plus 4 times 120. So that's 240 plus 480. So just double check that. So 240 plus 480 is 720. And over here I get 3 times 150 plus 4 times 50. So that's 200 plus 450, which is 650. And over here I get 3 times 150, which is 450. And the goal was to find the maximum value. So maximum value appears to be 720. So where is the function maximized? So it's maximized at the point 80, 20, 80, 120. What is the maximum value? The maximum value is 720. Okay. Challenge problem. So let's take a look at this. Ella is baking cookies for a bake sale to raise money for her favorite charity. She needs to make 2 kinds of cookies, ooey gooey chocolate chip and gluten-free oatmeal raisin. A box of chocolate chips costs $2, takes 15 minutes. A box of oatmeal costs $4 and takes 15 minutes. She has $40 she can spend on supplies and 240 minutes she can set aside for preparing and baking. From past experience, she knows that she needs twice as many boxes of chocolate chip as oatmeal raisin. She will make $5 per chocolate chip and $7 for oatmeal raisin. How many boxes of each type should she make? Okay, I start to get bogged down and I just go to the question. How many boxes of each type of cookie should she make? Okay, so I don't like variables to be O, so I'm not going to let O be oatmeal. So I'm just going to go with C for chocolate chip and R for raisin. So C is going to be the number of boxes of chocolate chip, and R is going to be the number of boxes of raisin. So I'm trying to maximize the amount of money that she makes. Okay, so her revenue. So I'm trying to max my revenue. So the revenue is going to be something C plus something R. Okay, the minute I define those variables as C and R, this becomes C and this becomes R. And I will always write them in that order. Okay, so C and R. So how do I make my money? I make $5 on a chocolate chip and I make $7 on the raisin cookies. So that's my objective function. Now, what are my constraints here? Okay, so my constraints. It looks like the constraints have to deal with time. Okay, so it looks like time that I have to make them. And cost, okay? So if I look at it, I've got cost and time, okay? So let's look at the cost. So I've got the variables are C and R. So from a cost, how much can I spend on supplies? It says that she can spend $40 on supplies, okay? So she can spend 40. It's okay to go up to it, but she cannot go over. So I got to spend less than 40 on my cost of supplies. So how much does it cost to make the chocolate chip? So it takes $2 to make the chocolate chip, and it costs $4 to make these special raisin cookies. Okay. And then time. She has 240 minutes. Okay, so I cannot go over 240 in my time. Okay, so I cannot go more than 240 in my time. And so how much time does it make for a chocolate? So it tells me it takes 15 minutes for oatmeal raisin. Chocolate is 15 and oatmeal raisin is 15. So both of these. So it takes 15 minutes for both of these. Okay. And then there is another constraint that I have. I will need to make, and this one's a little bit different. This is where the challenge comes in. She needs to make at least twice as many boxes of chocolate chip as she does a oatmeal raisin. Okay. So what's the relationship between, so this one you got to figure out. We've got raisin and chocolate chip. So, or let's see, let me do it in order consistently. Chocolate chip and raisin, okay? I need to make at least twice as many boxes of chocolate chip as I do of oatmeal raisin, okay? So that means if I were to double the number of raisins, that's how many chocolate I need to make or more. So the amount of chocolate cookies has to be more than twice the raisin. Okay, this sort of reads differently. Like if you make twice as many boxes of chocolate chip, you're going to have more chocolate chip than raisins. How many more? If you were to double the raisins, that's the least amount of chocolate you got to have. So you got to have more than that. So C is greater than 2R is the other equation that you're going to need there. So the other one you're going to have, so that's the other constraint. And then so the other constraint is that C is greater than equal to 2R. And this is a special constraint that gets thrown in. Okay? And now I'm ready to graph all of these guys. So if I come over to my graph, let's graph these functions. So I've got 2, 4, and 40. So I've got C greater than equal to 0, R greater than equal to 0, and then I've got 2, 4, and 40. So 2C plus 4R is greater than equal to 40. And then the other constraint was 15C plus 15R greater than equal to, I think it was 240. And then I got C is greater than 2R. Okay, so let's figure out what happens in each of these scenarios. So if I have C and R, if C is equal to 0, then R is equal to 10. If R is equal to 0, C is equal to 20. And in this case, C and R. And so if C is equal to 0, R is equal to 16. If R is equal to 0, C is equal to 16. Okay. And the next one here, this is the line C. You can think about it. This is the line Well, let's just do, I can't pick 0, 0. If R is 0, C is 0. So let's pick another couple of points. So what I'm going to do here is just say, okay, I've got C and R. Okay. And let's just say if R is equal to 1, then C is equal to 2. If R is equal to 5, C is equal to 10. Okay, so we know we've got that line. And so now let's just figure out where we go from here. Okay, looks like I need to scale my axis up to 20 in both cases. So we're going to do that by 5, 10, 15, 20, and 5, 10, 15, 20. So 0, 10, and 20, 0 is right here. And then 0, 16, and 16, 0. And then if I look at the line that goes through, say, if C is 2, R is 1, so 2, 1 is right here, and 10, 5 is right here. And if I look at that line, so something like something close to that, okay? Now, I got to look at this line. This is where C is equal to 2R, okay? So I know that the number of chocolate chips has to be more than twice the number of raisins, okay? So if, in this case, if the raisin number, so this is the tricky one. So you've got C equal to R is this line, okay? Where are the C values greater? Okay, so here if I've got 5 raisins, I got to get to 10 for my chocolate chips. I could be okay if I had more than that. Okay, so it tells me I'm shading below this line. I'm shading below the red line, and I'm shading above the green and the blue line. Okay, so in this case, I'm shading above that. So if you look at it, I'll be shading this area right here below this line, above both of these lines. Okay. So that's going to be my feasible region. And if I look at my vertices here, my vertices are going to be, there's one right there, the red and the green line, the blue and the green line, and this line right here. Okay, so I've got to figure out where these lines all intersect. So I'll take my calculator in just a moment and do that. So where the green and the red intersect, and then where the blue and the green intersect, so the blue and the green, okay. Okay, so let's figure this out. Where the red and the green lines intersect. So go to my calculator. So menu, algebra, solve, 2 variables. My variables are C, comma, R, and enter. And so I've got 15C plus 15R equal to 40. And then my next equation is going to be is C equal to R, and solve this, and I get what, 32 over 3 and 16 over 3. Okay, so in this case I've got